Hi everyone, welcome back to my Z80 computer series. In this series of videos, I'm attempting to build my own Z80 computer from scratch. So I'm continuing on with the VGA circuits, and in particular, I'm now looking at the timing of the control signals for the video RAM. Now, one major obstacle that I need to overcome for the video RAM is that we need to be able to share that RAM between the video circuitry and the CPU. Because only one thing can access the RAM at any one time, I'm going to have to come up with some kind of time sharing mechanism where some of the time the CPU is given access to the RAM and the rest of the time the video circuitry is given access to the RAM. Now, I've been looking at a design that was shared with me on Reddit. There is a lot of detail there in that design. There is very good documentation, not just the schematics, but there are block diagrams, detailed text explanation of each part of the circuit, as well as timing diagrams. So I've been studying that and having a look at the RAM control signals and how the timing for those signals work. So in particular, we've got four signals. We have a signal that indicates the CPU can access the RAM. We've got another signal that indicates the video circuitry can access the RAM. We've got a write signal and a read signal. So what I'm going to be doing in this video is I'm going to be looking over their design, the particular part of their schematic. I'm going to explain the principle of how that works. I'm going to dive quite deep into the actual timing. I'm going to be looking at different alternative ICs. And then I'm going to build it up on the breadboard, as we can see here. And I'm going to examine the signals on the oscilloscope so we can really see what's going on. So this is the part of the circuit that I want to look at. This is the RAM timing generation. Just to keep things a little simple for now, I'm going to be ignoring these two D-type latches. They are important, we will need them, but just for the moment I'm going to ignore them. I'm going to focus on the top part of this circuit here. Now we have, over on the left, we have the horizontal counts coming in. We have bits 0, 1 and 2 of the horizontal counts. And then we have this 138 chip, which is decoding our different stages. We have 8 different stages. Then we have some logic gates. There's 1, 2, 3, 4, 5, 6, 7, 8 different logic gates here. These are setting up all of our 4 signals, and then finally those signals get fed into this 374. It's just a latch, but the purpose of this is to retime those signals, because we have a bit of a problem with propagation delay. As the signals go through each chip, the outputs don't instantaneously reflect what the inputs are telling them to do. There is a small delay known as a propagation delay. So that's a delay from when the inputs change to when we see the change on the output. And that will happen for every device. So we'll get a delay here in the 138 chip, then we'll get another delay on these chips, and then we'll get more delays here, and then more delays here. So all of the signals appear at the end at slightly different times because they've gone through slightly different routes through these chips. So what the retiming chip is doing at the end is on the clock pulse. So we've got the clock here, pixel clock. All the input signals will be set up, and on the rising edge of the clock, they'll get latched into here. And because the output enable line, output enable is tied down to ground, the output's active all the time. So as soon as they are latched in, they'll all appear on the outputs here all at the same time. So that gets rid of all of those different propagation delays. There will still be a final propagation delay on this chip, but that will be the only one, and it will be the same for every single signal. So all the signals will appear at the same time. So that is really the only reason why we have this chip at the end. But it's quite an elegant design, really, because it's eliminated all of the differences in the timing signals and basically just aligned everything. Now we're going to see that on the oscilloscope at the end. I actually think it's quite a thing of beauty. It's really nice to see how you can see all your timing just slightly off, and then you pop this chip in and all your timing jumps into place. It looks really nice, and it doesn't really matter what it looks like. It's more, how it functions that's important. So I'm actually going to also be ignoring this inverter here. I believe this is an override. If I just very quickly run through the signals, just high level, this logic gate here is setting up the video signal. This one here is setting up, if you take the direct output of that, it comes across to the CPU signal. And then I believe that one also controls through this OR gate and this inverter the outputs, the read signal, the output enable, which is our read signal. And then the last one down here is for the write signal. It comes through this OR gate here, through an AND gate here, and then it comes through to the write signal. So these bottom three here are really the path that the write signal takes. And what we have here is we have the write request coming in from this D-type latch. I know I said I was going to ignore these, but I'll just very quickly show you what they're doing. The signal here, without explaining it, it just comes through this line here, through the latch. It goes actually around a loop, goes through the latch again, comes around here, through into this D-type latch, and eventually comes out here. And that's all I really wanted to say. The write request eventually will come out of this line here, and it goes into this OR gate. And bearing in mind that there is this sort of path through here is the write signal. It's this gate here, this signal coming in here to this OR gate that's sort of setting up to say the write signal will only be active when we see an input coming in here. And this is also an override. I believe it's an override to allow the fonts to be written into the RAM. I'm not going to have that on my design, so we can ignore that. And because we can ignore that, we can also ignore this chip here, because this is only here to have a point where we can actually bring the signal into the circuit to allow it to override it. This is an AND gate. So we can actually eliminate these two. So I'm actually going to redraw this, but it is essentially the same design. So this is my version, because I will want my own set of schematics, so I needed to redraw it anyway. And I've just eliminated the bits that we're not interested in today. So I've taken off those two D-type latches. We will have to add them back in at some point. And I've taken off that font override, and the AND gate is now missing from here. The signal just comes straight through. So it should be slightly easier to understand this. So what I'm going to do next is just look at each gate in turn and look at the function of each gate and the propagation delays of each gate. So these are our 4 signals, and what we're looking at here is the read cycle. This is kind of the default state of the system, the read cycle. And the blue areas are when the video circuitry has control of the RAM or has access to the RAM, and the orange shaded area is when the CPU has access to the RAM. Now you'll notice another very elegant part of this design is this gap in between, this white area in between when the video circuitry has access and when the CPU circuit has access. You'll see there's another one here as the cycle repeats. Now that is very deliberate. That's there to guarantee there's never any possibility of an overlap. So the video circuitry trying to access the RAM at the same time as the CPU circuitry. That can't happen because we have this full cycle where both lines are disabled. They're both high at that point. So the blue line here only drops low in periods 0, 1 and 2. That's when the video circuitry has access. And the orange line, the CPU line, only drops low in periods 4, 5 and 6. That's when the CPU has access. The right line at the top is always high because this is a read cycle. So the right line is always high and disabled. and the output enable, which is essentially when we're reading, when the video RAM is outputting its signal, that's always low during a read cycle. We're always outputting. If we look at the write cycle, we'll notice that the vid line and the CPU line are exactly the same, but this time the output enable gets turned off during periods 4, 5, and 6. And the write signal drops low during periods 5 and 6. So the outputting will be turned off, and then the write line will be turned low on the next period. So that's what we want our signals to look like. And we're hoping that we're going to see something like that when we look at the oscilloscope. Now the first chip in our little chain as we run across the circuit from left to right is the stage decoder, the 138 chip. That has in its inputs the horizontal counts, the bottom 3 bits of the horizontal counter, bits 0, 1, and 2. And if we look at the truth table, I've labeled them in reverse so that they represent binary numbers. So if you look at the first one is all zeros, and that's like representing the binary number 0, and then it goes 1, 2, 3, 4, 5, 6, and 7, and then the cycle will repeat. It will go back to 0 again. And at each stage, the relevant output line drops to 0. So on stage 0, the 0 output is low, and all the other outputs are high. On stage 1, the 1 output is low and all the other stages are high, and that just sort of repeats as you go through each stage. You kind of get this diagonal line of zeros across the truth table. As we go through each stage, that particular line drops low. And what I've shown down here at the bottom is the propagation delays, TPD. Now, these 7400 series logic chips actually are specified to operate over a very wide temperature range. So there can be some differences in the propagation delay depending on temperature. But as we're typically operating sort of at room temperature, we're not intending to take our Z80 computer out to the Arctic or to the Sahara Desert. We're going to be in sort of more comfortable temperatures. We're probably going to see figures that are lower than this. But I am trying to point out here that the AC version of the chip is about 4 times faster than the HC version. Now, I've used the HC version of the chips up until now, but I think at this point in the design, it's starting to become important. Timing is quite critical here, and we may have to start using some AC versions of the chips. The next gate that we have to go through is the 3-input AND gate. And again, I've shown the truth table, and actually the inputs here are identical to the 3 inputs on the 138 chip we just looked at. So we can have 8 possible values, 0 through to 8. And because it's an AND gate, the output will only be high when all of the inputs are high. Now, something interesting to observe with logic gates is when you're interested in the low value, the gate kind of takes on the opposite function to what its name implies. So because we're interested in when the output goes low, the output can only go low if any one of the 3 inputs are low. It's only high when all of the inputs are high. So if any one of the inputs are low, we're going to get a low. Now that's actually like an OR gate. If A is low, or B is low, or C is low, then we get a low on the output. So because we're kind of inverting the logic here, we're thinking about the low signals rather than the high signals, the gate kind of takes on a different function and kind of acts more like an OR gate for the zeros. Again, I'm showing here the propagation delays. This is a little bit faster chip. The HC part has a maximum propagation delay of 25 nanoseconds, and the AC part has a maximum propagation delay of 8.5 nanoseconds. The next gate I'm going to look at is the 7408. This is a 2 input AND gate. Exactly the same principle. Because we're interested in the zeros, it kind of takes on the function of an OR gate. So if A is low or B is low, then Y will be low. Again, we have the exact same propagation delays, 25 nanoseconds for the HC part and 8.5 nanoseconds maximum for the AC part. Now we do actually have an OR gate. It's 7432. And the same thing is true here. The output is high when either of the two inputs are high. So if A is high or B is high, then the output will be high. Now, if you look at the truth table, the only way the output can be low is when A is low and B is low. So although its name is an OR gate, because we're interested in the zero value, kind of acts a bit like an AND gate. When A is low and B is low, that's when we get low on the output. So it's kind of, you have to flip your thinking over when you're looking at the zeros. The AND gate kind of becomes an OR gate, and the OR gate kind of becomes an AND gate. Again, propagation delays. I think they were the same, weren't they? 25 nanoseconds and 8.5 nanoseconds. Finally, we have the inverter. It's the simplest of the logic gates. Very simple truth table. Y is the opposite of A. So A being the input and Y being the output. If A is low, Y is high. And if A is high, Y is low. Not really much more to say about that. This is actually, because it's a simple gate, it's actually the fastest of all the gates. 24 nanoseconds for the HC part and 7 nanoseconds for the AC part. Now what I've done is I've added up all of those potential propagation delays. All of the signals will have to go through the 138 chip. So I've included that in all of them. They will also all have to go through the 7411 chip. So I've included those. The write signal and the output enable signal have to go through the 7432 chip. And the write signal is the only one that has to go through the 7408. And the output enable is the only one that has to go through the 7404. So I've added all the times up. My red numbers are for the HC parts and my green numbers are for the AC parts. And we can see if we add up all the red numbers for the write signal, I think that's the worst case, it actually comes to a total of 120 nanoseconds. Now again, bear in mind that's the maximum value, and as we're not operating at extreme temperatures, we probably would come in actually considerably less than that. But we are technically quite a bit out of our specification because we need to be under 100 nanoseconds, and the maximum we could have here as being 120 is quite a long way out of our specification. Very similar story for the output enable line coming in at 119 nanoseconds. But the vid line and the CPU line are actually okay at 70 nanoseconds. On the original design, which we're kind of referencing or copying, that clock was operating at 25 megahertz, just over 25 megahertz. So their period time was just under 40 nanoseconds, about 39 nanoseconds, I think. So this would actually well exceed their design, but because my clock is slower, I'm going to be okay with these 70 nanoseconds. But these top two are probably pushing my luck too far to use HC parts for these top signals. Now, the slowest chip of all of them is the 138, coming in at 45 nanoseconds for the HC part. So that would be the one to definitely require an AC part. So I'll definitely use an AC part for that one. And as it turns out, I actually don't have any HC versions of the 7411. I only have the AC versions. So we'll also use an AC version for the 7411. But the other chips, the 32, the 04 and the 08, I will use HC parts. And mainly that is just to demonstrate the problem on the oscilloscope. In the final design, I probably will just use AC parts for everything. But the main point here is to just bring our attention to the total propagation delay and why it's important to use AC parts over HC parts. So that's enough theory. Let's jump onto the breadboard and start looking at some practical stuff.
So I've got it built up on the breadboard here. I mean, you can barely see the chips through all the mess of wires. It isn't too bad. So over on the left here, we've got the 138, the stage decoder. The next chip along is the 3-input AND gate. That's the 7411. The next one along is the 7408. That's the 2-input AND gate. Then we got the 7432. That's the 2-input OR gate. And then finally the last one is the inverter, the 7404. That's all the logic chips. And then we do finally have the 374 latch at the end. Now I've got my oscilloscope probes connected to the inputs of the latch, so we could see what the circuits, what the timing signals would look like if we didn't have the latch, or what they look like up until the point they reach the latch. One thing I will mention is this little board here. I had some problems. I was originally using my timing board here, and I've got rid of that for the moment and just switched to a much simpler timing circuit here. I think there were some problems with the reset on that timing board, and I was seeing a lot of ghosting on the oscilloscope, so I just wanted to just get rid of that to give us some nice clean signals to look at. And I probably need to go back and look at that timing board at some point. So all I've got here is a 10 megahertz crystal, and that's just feeding this counter. This is a 163 counter. It's just given us some counts out of here. This will just simulate our first 3 bits of the horizontal counter. And that is also connected through the white wire up to the clock on the latch, because the latch needs to be synchronized with our clock. So if I show you what we've got on the oscilloscope. So this is the first signal I've got on the oscilloscope, the blue line here. You can see it's dropping low for 3 periods, and then it's high for 5 periods. So that is the 8 periods that we're expecting. And if I zoom out, you can see that signal just keeps repeating. But if I put my scale, which my horizontal scale here is 100 nanoseconds per division. So each one of these squares is 100 nanoseconds, and the signal does appear to be switching nicely exactly on the periods as we're expecting. If I bring in the next signal, this is the CPU signal, and again it's dropping low for 3 periods, but that is happening later than the video signal. And if I overlay the two, let's just bring that down here. This again is exactly as we expect. We see the video signal drops for 3 periods, and then both the lines are high for 1 period, and then the CPU line drops for 3 periods, and then again they both go high for 1 period. And these are the gaps that we saw on the slides I showed you previously. They were the white gaps between where the video signal had access to the RAM and where the CPU signal has access to the RAM. And by having this 1 period gap in between, you can see quite clearly from this that there could never possibly be any overlap where both signals are trying to access the RAM at the same time. So that's nice. I'm going to move that back up to where it was. And I'll bring in the next one. There we go. So that is the right line, and it's actually high all the time. I think you can see from the little indicator at the left here. I think that's like its 0 reference point. So you should be able to tell from that the signal is actually currently high all the time, and that's the right line, so it's disabled. So what we're looking at here is a read cycle. If I bring in the read line as well, and we can see there that the read line is actually low all the time. So the read line is active all the time. So again, it's exactly what we're expecting to see. If I move this little wire here, we can simulate a write cycle. And you can see what's happened as the read line actually goes high, it's disabled for 3 periods. Then it re-enables again. And the write signal goes low, so it actually activates the write signal for 2 periods. And it happens, the write line drops to 0 1 period after the read has been disabled. So again, it all matches up with what our timing diagrams were expecting. Now, you may have already noticed the problem. You can see that the yellow line and the purple line, they're not lined up with the grid. If I zoom in a little bit to exaggerate it, there. So you can see that the yellow line is dropping low, but it's quite a bit after when the period actually starts. And I can measure that. So the first cursor line is actually lined up with the grid line, so it's when the period starts, and then the dashed line is lined up with the yellow signal when it's dropping low. And if we look over here at BX minus AX, it's telling us that that little gap in there is 19 nanoseconds. Now, I can't remember what the figures were when we were looking at the propagation delays, but we do have to bear in mind that those numbers that I was showing you were the maximum values. So our propagation delay here is probably a little bit less than what those maximums were telling us. But I'm really just trying to emphasize the problem. You can see that the propagation delays are actually causing the signals to happen a little bit later than when we really want them to be. And the purple line is suffering from the same problem. If I just get rid of these cursors off, I'll zoom back out to where we were. So these are the signals that are going into the latch on the breadboard. So that's what it would look like if we didn't have that retiming latch at the end. Now what I'll do next is I'll pause the scope. I'm going to move the probes to the outputs of the latch, and then we'll re-enable the scope and see what happens to the signals. Okay, so I have moved the probes. If I hit the single button on the oscilloscope, the button over here, we should get a new capture. And you particularly want to watch the yellow line here. So if I press that, boom, everything is now lining up with the grid lines. You see the yellow lines lining up with the grid line, purple lines lining up with the grid line, same where it drops at the other end as well. Everything is now perfectly aligned with the grid lines. Now that is the effect of that retiming latch at the end. It's difficult to tell on the scope, but everything's actually shifted 1 period forward, I think, forward or backwards, I'm not sure which, but it's moved 1 period, but you can't really tell that on the scope. But they should all be in the right positions. I think we could probably probe horizontal count 0 to have a look at that, but I'd have to lose one of the signals. If I take the purple signal, I guess, I'll just leave it running, take the purple signal off, And if I pop that, if it will reach over to the first count. So the purple signal is now actually our, that's still difficult to tell, I think, isn't it? That's the first, well, we can't really tell because we don't know which one is the first period. This is better, isn't it? This is horizontal count 3. So, or bit 3 of the horizontal counter. So it's actually low for 4 periods and then high for 4 periods. So this is our start. This is our first period starting here. So we get 1, 2, 3, 4, 5, 6, 7, 8. Or I think it's actually numbered 0 to 7. This actually is really the start of our period. The inputs, the horizontal counter. And if I did, I think I'd have to move the trigger a little. No. It's this one, is it? Get there in the end. So yeah, so that's actually the purple line is lined up with the grid lines, and we do have a small piece of propagation delay, and that will be our final latch propagation delay. But it's at least brought all the signals in line with respect to each other. So I'm pretty happy with that. Feel like I quite deeply understand this circuit now. Studied this circuit quite a lot now. Got a good understanding of it. And I have got on the oscilloscope what I'm expecting. Don't always get that. Kind of get some, normally, sometimes you can get some surprises once you come to the oscilloscope and start actually measuring things. Okay, so I think where I'd like to go next is try and see if we can pull all of this together. I've looked at quite a lot of different aspects of the VGA circuitry now. I've looked at the horizontal and vertical sync pulse timing. I've looked at the pixel shifting, which didn't work great, but we did get some success with it. And this work here may give me some better understanding of how I might be able to improve that. We also looked at how we can try and share the access with the CPU by using some additional registers. And then finally we've looked at this video RAM timing generation circuits. So we've got a lot of the different pieces of the puzzle, so it's just really a case of plugging everything together now, see if we can get the whole thing working as one. I don't think I'm 100% there. I think there's still a few more little bits I need to iron out, but I feel like I'm making some good progress on this now. So we'll leave this here. Thank you for watching, and I'll see you in the next one.